Okay, so hello everyone. So today we will first finish the divided difference and the lower order interpolation. And after that, I will show you several pictures and show you why we should consider some higher order interpolation. So that means not only do we fit the function value or just yi points, and also we need to consider the derivative at those points. Okay. But before that, we need to first finish the divided difference, and we have some more examples to show and one key theorem. Okay, so remember, if we review a little bit about what we did last time, so one very important properties we discuss is the important theorem we discuss is about invariant properties of the divided difference. Okay, so particularly we show that the divided difference this guy fx 0 up to xk, this guy is invariant to the permutation of the arguments x0 up to xk. Okay, so what does this mean? So this basically means that if you change the order of this x0 up to xk, so for example, you have x0 prime up to xk prime, so this guy essentially is equal to fx0 up to xk. Okay, so this one basically is a new permutation of the same data set. Okay, so what does this mean? So basically that means now suppose we have a data set x0, y0, and xn, yn, and now let me just do this xn plus 1 and yn plus 1. Okay, so basically that means if we first consider the interpolating polynomial based on this data set, and then later we add one more point, this is equivalent to we consider basically all the n plus 2 points, I mean just from 0 to n point to n plus 1 points, all n plus 2 points here together. Okay, so or this is firstly consider n plus 1 point and add one more point. So this guy essentially gave us the same result as we consider n plus 2 points interpolation directly and also all together. Okay, so for this case, essentially that is the case we want. So that means, for example, we are given n points, and this is basically we can fit a polynomial or basically a Newton basis polynomial that satisfy all n plus 1 points over here. But now in the real application, once the research scientist or the engineers collect one more point, so essentially we can use the current this n plus 1 point interpolation to update this interpolation. Turns out we will have the new interpolation which also take into consideration of this n plus 1 this xn plus 1 yn plus 1 point. Okay, so this essentially is the same as we do everything together, but in the real application we don't have this n plus 2 point at the beginning. We usually only have firstly n plus 1 point and some new information. But the theorem over here essentially shows that if we do this separately, it is equal to we do everything together. So this is a rough idea about why we consider the Newton basis, and essentially that means we can do adding one more point very easily. Okay, so this is very abstract way to say this, and we can just consider one simple example, and I think you will understand this easily. Okay, so this example is not in your textbook, so maybe you need to take a note. Okay, so still this time we have 3 points, x0, y0 is equal to 1, 2, and x1, y1, is equal to 2, 3, and x2, y2, this guy is equal to 4 and 5. Okay, so basically 3 points. And the question basically is use 3 points and construct the polynomial and using the divided difference. Okay, so use the divided difference to construct the interpolation polynomial to the data set, basically in Newton basis, in the Newton's basis. Okay, so the question is just given 3 points, and we need to consider Newton basis in polynomial interpolation. And but here, instead of using the linear system or solving the lower triangular system, we consider the divided difference. Okay, so to do this, and we just need to use our divided difference table, right? So let me just move to a new page and plot this. So for this very big table, okay, so here we need to put x, and here is the first difference. And then here we have the second difference, basically xi plus 1, right? So we can remember we can also do the subscript over here. And the last one is f xi plus 1 xi plus 2. Okay, so I'm running out of space, but I think it should be fine. So for the x is the x coordinate of 3 points we have. So essentially we have 1, 2, 4. Hopefully, yeah, should be okay. So fxi, so the first difference, so essentially this guy are just the y coordinates corresponding to the x value, right? So this guy essentially is also equal to f of xi, but parentheses. Okay, so if you copy the point, here is equal to 2, here is equal to 3, here is equal to 5. Okay, so now the first difference. So according to the definition, so the first difference, this guy essentially is computed as f xi plus 1 minus f of xi over xi plus 1 minus xi. Okay, so remember this is also called a forward difference, and we need to leverage this one and this one and this one to compute this first difference. Okay, but we have 2 pairs. So for the first pair basically depends on these 2. Right, so we will have this is equal to f of x1 minus f of x0 over x1 minus x0. So this gives us 3 minus 2 over 2 minus 1. So this essentially is equal to 1. Okay, so the first pair in the first difference, and now we need to compute the second pair of the first difference. So this guy essentially is equal to f of x2 minus f of x1 over x2 minus x1. So basically this one gives us, if we substitute the value, we have 5 minus 3 over 4 minus 2, which is also equal to 1. Okay, so another thing is, if you like, here you can change this notation to the square bracket, right? So basically, if we do this, I think we will focus on the recursive definition of the divided difference. Okay, so but the square bracket is equal to the parentheses if we only consider one argument divided difference. Okay, so now for the second difference, so firstly, still by the definition, so this guy is equal to we need to define this recursively. So that means we need the first difference. So this guy will be xi plus 1 minus f. Oh no, sorry. This is equal to. So this is equal to f xi plus 1, xi plus 2 minus xi plus 1 over xi plus 2 minus xi. Okay, and also remember for this guy, we can also do the subscript, right? So this will be xi plus 2. So I will write this down later. So because I don't want to do this index subscript, it's very complicated. Okay, but based on the definition over here, we can just compute this xi. We can compute our target, which is over here, right? So this guy essentially is equal to f. Our I is equal to 0. So here will be x1, x2 minus f x0, x1 over x2 minus x1, and this guy is equal to 1 minus 1 over x2 is equal to 4 minus 1. So essentially it's equal to 0. Okay, so basically we need to rely on the first difference. Okay, however, here I remember I said the subscript, so this one you can also write this as f12, this is f01. Okay, this is much easier than rewriting this way. Okay, so based on the information over here, we can finally give the polynomial interpolation. Okay, but essentially the formula for this p and x constructed in the divide difference has such kind of form, right? The first one and the first difference times x minus x0 and then plus f x0, x1, x2, and here will be x minus x0, x minus x1, right? And up to infinity. Okay, so this is or let me just write the last term. So last term basically is f all the difference x0 up to x0 up to xn, and here's x minus x0 up to x minus xn minus 1. Okay, so remember for the Newton basis we stop at n minus 1 instead of n. Okay, so but here we only have 3 points, right? So remember n is equal to the number of point minus 1. So we have p2 of x, and this guy essentially we only have the first 3 terms. So fx0 is equal to 2. Fx0 is equal to 2, and then we just need to plus fx0 fx1. So this essentially is fx0. It is this one, right? So this guy is equal to 1, and then times x minus x1. So x minus x1 is equal to 1. So finally we have this is equal to x plus 1, right? So this is basically p2x. So I didn't write the third term. So actually we also have a f x0, x1, x2 times x minus x0, x minus x1. But this one basically vanished to 0 because we already calculated over here. Okay, so this is a p2x, and this one basically is what we did before. But now we have the second part of the question. That is the part B of the question is given a new point. Let's say what is our new point is x3, y3, which is equal to 5, 8, and then compute the Newton's interpolation for all 4 points. Okay, so we have a new point over here, and we need to compute the Newton's interpolation, not for this new point, but for all 4 points we have. That means we also need to include this x0, y0, x1, y1, and x2, y2, these 3 points plus this 1 point. Okay, so and in the question it already specified we need to consider the Newton interpolation. However, remember we also have some other choices, right? So in your exam or in your homework, we may not see that compute the Newton interpolation. Instead, it will only ask you to compute the interpolation. And in this case, this may be a little bit, you need to know that the easiest way basically is the Newton interpolation. Okay, so the reason is we can use the divided difference, and we just need to compute the partial information. Okay, so how can we do this? And why the other, for example, the Lagrange interpolation may not be work, and we will do it now. But let's first show that how can we compute the Newton interpolation for all 4 points given the new information. So according to the formulas over here, okay, so we this one is invariant to the how can we say, the permutation. So that means if we consider the next term, okay, so or we have one more point, so essentially we just need to compute f x0, x1, x2, x3, and here will be x minus x0, x minus x1, x minus x2, right? So we will stop here because we only have n equal to 3 or 4 data points. Okay, but if you check the formula, all the terms over here, well, does not change, or they will not be affected by the given new point, which is x3 by 3, right? So everything over here only relies on the points information of the first two. So that means we just need to compute this guy. Okay, but for this part, essentially, yeah, it's pretty much given. We just need to consider the divided difference. And this guy is defined recursively, so that means we need several other divided difference. Okay, so particularly, we need to first compute this f x2, x3, right? Because we need to use this one to compute the third difference, which is x1, x2, x3, right? But firstly, according to the definition, this one is equal to f x3 minus f x2 over x3 minus x2. But f x3 is equal to 5, and f x2 is equal to no, f x2 is equal to 5. So this one, f x3 is equal to 8, right? So it is given over here. So this is 8 minus 5 over 5 minus x2 is equal to 2. So x2 is equal to 4. So it turns out this is equal to, this is 4. So it turns out this is equal to 3. Okay, so once we have fx2, fx3, so we can compute fx1, x2, x3, right? But according to the definition, this is equal to f2, 3 minus f1, 2 over x3 minus x2, right? But we have everything on hand. So this guy is equal to this f1, 2. We already computed in the table, so which is this guy, right? And then for the coordinate information, we also have it. So, no, sorry, I made a mistake. So this is x3 minus x1. So turns out this will be 8 f2, 3 is equal to, f2, 3 is equal to 3. So it is just this number. We just computed f1, 2. We need to go to the table, so which is equal to this number, right? This is 1, 2. It's this one. This is 1 and 2. So it's equal to 1. So then later this will be 3 minus 1. And here will be x3 is equal to 5. I remember this number. x1 is equal to 2. Okay, so turns out this is equal to 2 over 3. Okay, so this is f1, 2, 3. So this is f1, 2, 3. Okay, so now essentially we can just try to construct our x0, x1, x2, x3, right? The targets or the only new divided difference we need to compute. But or if you like the simplified notation, this is f0, 1, 2, 3. But by the recursive definition, this guy is equal to f1, 2, 3 minus f0, 1, 2, right? f1, 2, 3, f0, 1, 2, yes, I'm right, and divided by f3, x3 minus x0. Okay, but we have every number ready, so f1, 2, 3, we just compute it, which is equal to 2 over 3. So which is copy over here, and f0, 1, 2 we computed in the table, which is equal to 0, right? So x3 minus x0 will be 5 minus x0 is equal to 1, so turns out this is equal to 4, so this will be equal to 1 over 6. Okay, so once we have this, we can just try to write down our new polynomial. So this time we have p3 of x. This essentially is equal to p2 of x, which we can just copy, and then plus the new term, which is 1 over 6, and x minus 1, x minus 2, and x minus 4. Okay, so we are done with this example. So basically we just add one more point, but you can see that for most of the information we don't need to compute, because for p3 of x, this part is p2 of x, so we just need to compute one more new things over here, or particularly we just need to compute the new divided difference, which relies on the previous divided difference. So we just need to consider the difference, which is x0, 1, 2, 3. Okay, so this is just about the P3. And then another question is why for example, we also discussed the Lagrange. Why this one is not easy given the new point. I think this is straightforward, right? So basically, if you are given the new point and for the Lagrange polynomial, so for example, we need to compute x0, x minus x0, x minus x1, x minus x2, and x minus x3. So for the first Lagrange polynomial, we don't have or L0. So the new L0, essentially we need to compute the new terms over here, right? Or on the bottom we have x0 minus x1, x0 minus x2, and x0 minus x3, right? So that means, well, this is a new one, but given a new term, so essentially we need to have x minus x3 and x0 minus x3. But it turns out if we simplify this, we need to completely recompute this product. Okay, so that means adding a new point will be difficult for the Lagrange polynomial. Okay, so or this is why the Newton basis is more easy if we consider new point, which is very common in the real application. And also we can just using the divided difference to do this because of it is invariant to the permutation. Okay, so this is basically about the example, and thank you.